Hello and welcome everyone to EC3030. So in this video lecture we will continue our discussion on the interconnects. So in this video lecture we will look into the delay in interconnects more thoroughly, and what we have said in the previous lecture is that one of the techniques to reduce the delay in interconnects, the global interconnects, is to use buffering, and this is what we will mostly focus on in this lecture. Alright, so as we have said in the previous lecture that as we are making the devices smaller and smaller, we are putting more and more devices, and as a result what is happening is that the total length of the wires or the interconnects is also increasing. And important point that we made is that as we scale down devices, the devices become faster, but the interconnects actually become slower, which means that interconnect is becoming a bottleneck in our future electronics and digital systems. Alright, so what we said in the previous lecture is that as we scale down our devices, the gate delay becomes faster, but the longest interconnect delay actually increases as we go towards smaller technology nodes. And the reason is that there are concepts of local and global interconnects. Now local interconnects is the interconnect within a block, and that actually becomes smaller, and what we have said is that the delay in the local interconnect with scaling actually remains the same, but the delay associated with the global interconnects actually increases because the lengths becomes thinner, at the same time becomes longer, and this is why the delay in the longest interconnects become larger as we scale down our devices. Alright, so this is the framework that we presented. So we essentially said that, for example, if we have a metal layer over here, the resistance is given by rho L over WH, where W is the width and H is the height, and length is the total length of the wire. And then we have capacitance between the wire and the ground, which is represented by this one, and then also we have capacitance between the wires in the same metal layer, and also we have additional capacitances between this layer and the layer on top. Okay, so here it can be another metal layer, this can be ground plane or whatever, but essentially the thing is that all these capacitances are there. And one of the important point that we made is that the total line delay is proportional to the line resistance multiplied with the line capacitance. So this is what we meant. So what we have seen is that interconnects, there is a resistance associated with this interconnect, as well as all these capacitances are associated with it. And the important thing to note here is that these resistance and capacitance are distributed, meaning that if you want to create a model of this interconnect, it will essentially look like an RC network that looks like this. So you have resistance, capacitance, and one section that looks like this, and this is repeated many times along as you go from one end to the other one. Or for example, if you go from this end to all the way to the other end, the circuit will essentially look like this. And this is in electromagnetism, this is actually called the transmission line. And the significance of this representation of the interconnect is that as the signal gets transmitted along the x direction of this transmission line, not only once a signal is input here, it will take some time for the signal to come at this point. Not only that, the shape of the wave of the signal will also get distorted. So let me tell you what I mean. So let's say at time t equals to 0, an input is applied at this point over here, and the input looks like this, and the x-axis is x. Say at some time t equals t1, this signal comes to say here, and the signal will actually look something like this. It will get distorted, it will not have sharp edges. And say at time t equals to delta, it reaches here, and by the time it reaches here, it will get more diffuse, meaning that the signal will get distorted. And this phenomena, that there is a delay, meaning that it takes some amount of time delta for the signal to reach the other end of the wire. That is one phenomena. And the second phenomena is that the wave shape also get distorted. So this is the essence of the transmission line analysis. Transmission line analysis says that when you have a long wire, because of the distributed resistance and capacitance, there will be a delay associated with it, and as well as there will be a distortion of the wave. Alright, so this is the Elmore model of delay, and what Elmore model says is that if you have a transmission line that is represented by a circuit like this, then the delay will be given by this equation over here. We'll shortly explain what this equation means, but essentially what it says that delay will have a form like this. So let's look at this representation of the length of the interconnect. Now each of the sections represent a certain length of the wire. Say this can be, say, 0.1 micron, so a small region, small segment, or the small section of the wire, say 0.1 micron, is represented by this RC circuit over here. And say you have 1,000 sections, meaning that the total length of the wire is 0.1 micron multiplied with 1000, which gives you 100 micron. So what we have done is that we have represented 100 micron length wire by breaking it into 1000 pieces, and each of the piece is represented by an RC network like this, and each of the piece is represented by a RC network that looks like this, and we have 1,000 of these pieces. So what we said is that the total, so each of this segment is 0.1 micron, and say there are 1,000 of these segments. So essentially the total length of the interconnect is 100 micron. Again, we took a 100 micron long interconnect, and then we broke it into 1,000 segments, where each of the segments is represented by 0.1 micron of length. So we can also break it into 10 power 4 pieces, and where each of the piece will be represented by 0.01 microns. But anyway, we'll see how that affects overall picture, but let's get started with the model. Alright, so the delay is given by this equation over here, and let's say each of the segment is represented by a constant resistance, meaning that this R1 equals to R, this R2 equals to R, R3, all of these are given by the same value R, and the C's are given by the same C. So basically we have broken the entire system into equal sections, sections of equal resistance and capacitance. Alright, so this equation says that delta E will be given by Ci smaller than I n multiplied with 1j over I. Alright, so let's consider the first segment over here. So for the first segment, it will be C1 R1. For the second segment, it will be C2 plus R1 plus R2. For the third segment, it will be C3 plus R1 plus R2 plus R3, and it will go on, and the last term will be Cn multiplied with R1, or say Rk, where k goes from 1 to n. Alright, so now all the C's are the same, so essentially you have C here and R, so this will be R1, so an R1 is 1, so second one is C2 is C, and there R1 plus R2 is 2R, similarly C into 3R, and finally Cn is equal to C, and sum of all the r's is simply nr. So then if you just multiply them, Cr 1 plus 2 plus 3 all the way to n, and this essentially gives you this equation, that n into n plus 1. Alright. So now the delay due to the transmission line effect, the distributed resistance and capacitance, is given by this equation, half r c n into n plus 1. Now note what is n. N is the number of segments. So if you have, in this particular case, if you have 100 micron length, we have said that each of the segment is 0.1 micron. So n will be equal to 10 power 3. On the other hand, let's say you have another case where the total length is 200 microns, and for 200 microns each of the segment you say is 0.1. So in this case n will be 2 into 10 power 3 sections. And now you can clearly see that this delay is proportional to n square, which means that the delay will actually be proportional to the square of the total length of the where. So Elmore model directly says that the delay will scale as the square of the length, not linearly with the length. So that's one of the important points of the distributed nature of the resistance and capacitance in an interconnect, global interconnect. Alright, so we'll look into an example here, but before the example, what we want to introduce is a concept called sheet resistance. So sheet resistance, and sheet resistance is essentially a measure of the resistance of a thin film of a metal layer. So say you have a metal layer which has a thickness of T here, and the other two dimensions are W and L, and say current is flowing in this direction or this direction over here, basically the perpendicular to the dimension that is represented by T. And in that case so the current is actually flowing perpendicular to the direction, perpendicular to the cross section given by area W multiplied with T. So this cross section. So the resistance is rho L over L, rho L over A, and A is WT, and this term over here, rho over T, is defined as the sheet resistance Rs. So in other words, the thickness information goes into the sheet resistance over here. So the total resistance of a wire of length L and W with a thickness of T is given by this equation, sheet resistance multiplied with length over width, and this sheet resistance over here is given by the resistivity over the thickness. Alright. So we need to remember this equation, R equals Rs multiplied with L over W. Alright, so let's look at the example of a short wire, and in this wire the total length is 100 micron, and and the width W is 0.1 micron and the length is 100 micron. And we are also given the thickness information in terms of sheet resistance, and the sheet resistance is 0.04 ohms, and also the capacitance per unit area is 50 attofarad per micron square. Now what we are going to do for this analysis is that we are going to divide the entire length into sections of 1 micron length. So if you have a 1 micron long interconnect, the small r, which is the resistance of that section, so let's call it a section. So section is r, so this is the sheet resistance multiplied length over width, and length for this small section is 1 micron and the width is 0.1 micron. So the resistance of this small section is given by 0, is equal to 0.4 ohms. And the capacitance is essentially capacitance per unit area multiplied with width and length. So the width is 0.1 1 micron and length is 1 micron. As a result, the total capacitance comes out to be 5 attofarad. And we had a length of 100 microns, so and each of the section was 1 micron. So the total number of sections is 100. And if you plug all the numbers in, then the delta, the delay, will come out to be 10 femtoseconds. Alright, so remember that this number 10 femtoseconds. Now let's consider another case where the length is now 10 power 4 microns. In the previous case it was 100 microns. So let's say the previous case the length was 100 microns and the delay was 10 femtoseconds. Alright, now the length is 10 power 4 microns, 10,000 micron, and the width is remaining the same, 0.1 micron. Now again we are dividing it into 10 power 4 segments. Each segment of length is with length of 1 micron. So again everything will remain the same. The resistance of each section will be 0.4 ohms and the capacitance of each section will be 5 attofarads. Only thing is that since the total length is 10 power 4 microns and each of the section is 1 micron, we get a total number of sections with 10 power 4, and if we plug in the numbers, the total delay will come out to be 100 picoseconds. Now remember, for the previous case our L was 100 microns and the delay was 10 femtoseconds. Now we have increased the length by 100 times, but our delay has increased more than 100 times, and this is the essence of the problem, that as we go to longer wires, the delay also increases significantly. All right. So now one interesting way of reducing the delay is to use a buffer. So the concept of buffer is that, say you have a long wire, say the wire is 100 microns. So what you will do is you will break it up into multiple pieces and insert a buffer in between them. Now what the buffer will do is that, for example, you put in a signal over here or a signal over here. By the time it comes here, it gets diffused like this and there is a delay associated with it. Now by putting in a buffer in between, what you do is that this buffer makes the wave shape, it reshapes it so that it looks good, and then it passes to the next wire, and by the end of it, what essentially it does is that by the end, from here to here, first of all, the wave shape is not as bad as it would have been if there were no buffer, and in the process of adding the buffer you also reduce the delay in most cases. So that's what we are going to see in the next 2 slides. So what we are going to see is that how many buffers should we include to reduce the delay. So it happens so that if you if the total number of buffers that you add, or the total number of segments that you break a long wire into, if that number is small or smaller than a certain value, you will actually improve the delay. But if the number of buffers that you introduce is larger than a critical value, then it will again start increasing the delay in your interconnect. So that's what we are going to see. All right, so let's look into a particular case where we have a long piece of interconnect or a wire which is broken into multiple segments, and this is say one segment, and say this is another segment, and there are multiple segments like this. We are trying to see what is the optimum number of segments that we should put in, and within this each segment, say we have this segment, the transmission line corresponding to this segment is represented by this equivalent RC network over here, and what we will see is that each of this is considered one section of this segment. Also note that there is a resistance here, and this resistance represent the output resistance of this buffer here, and there is an additional capacitance at the other end which represents the input capacitance of the other buffer. Alright, so now let's say how this delay equation can be derived for this system. So the first segment is this one over here. So this segment also introduces RB, so it will be C multiplied with R plus RB. So this is the first segment. For the second segment, we have this capacitance C multiplied with, we have two R's and then the RB over here, so it's capital RB, and so on and so forth. For the third segment over here, you will have 3R plus RB, and we keep on going. So this is the n minus 1 segment. So for the n minus 1 segment, it will be so it's n naught. So n naught is the total number of sections within each segment. So it will be n minus 1 R plus RB, and finally for the last segment, it has two capacitances, C plus CB. So it will be C plus CB multiplied with total number of resistances are NR, N naught R plus RB. Now if you just take this equation, you will see that C, so if you take all the C's, so then it will be equal to N naught RB plus, you have R, 2R, 3R all the way to N naught R. So if you sum them up, you will get N naught plus 1 over 2 multiplied with R, and then what you will be left with is CB multiplied with N naught R plus RB, and this is essentially the equation over here. So again, this represent the delay of each individual segments. Alright, so let's look into the total delay of the interconnect. So again, what we have said is that each of this is one segment, so each of this is one segment, and within each segment there are total n naught number of sections. Each of these are sections, and this circuit is representing one segment. Now the delay of each individual segment is given by this equation. Now say the total number of segments is ns, meaning that there are n segments in the entire wire, and so if there are total n number of sections in the wires, so then the n will be equal to number of sections within each segment multiplied with the number of segments. So in other words, the total number of segments n naught is given by n over ns. Ns is again number of segments or total number of buffers. Okay, so the total delay will be equal to the delay of each individual segment, which is essentially this equation. This term is equal to this. So delay of each individual segment multiplied with the total number of segments that you have. So it will be an equation like this. Alright. So now let's say how the delay changes as a function of the number of segments. So in the x-axis we have, in the y-axis we have the delay, and the x-axis we have the number of segments ns. Now clearly what you can see is that if you introduce one buffer, if you introduce 1 to 2, you see the delay decreases significantly and you reach a minima for a certain number of segments. But if you increase the number of segments beyond that, then the delay will start again increasing. So intuitively, why does it happen? So the reason it happens is because that when n is small, you get the benefits from the scaling of this term over here, because it goes down as a function of x squared. Alright, but as you go on increasing ns, then at some point this CBRB term becomes larger. Now CBRB term comes from the output resistance and input capacitance of the buffers. So essentially, when you go beyond a certain number of buffers, you get dominated by the delay of the buffers themselves. So if you introduced a small number of buffers or break this interconnect into a small number of sections, the buffers, you reduce the delay because it reduces this square term over here. But beyond a certain number or a bit beyond a critical number of buffers, increasing the number of segments does not decrease your delay, rather it increases, because the buffer delay then dominates, and that's that.